Now, let's take a look at the law of total probability. It is a powerful tool that relates marginal probabilities to conditional probabilities. As a result, if we want to find the probability of A, we sum all of the probabilities of A intersection B. Because intersection probabilities are calculating using multiplication through the magic of math, it can be shown that this is the same as summing the conditional probability A given B and the overall probability of B. Let's take a look at an example to illustrate this. Imagine that you purchase a pair of hiking boots. If the boots are manufactured in country A, the probability that they will last 1,000 miles before the waterproofing wears out is 99%. However, if they're manufactured in country B, the probability is 95%. We know that 75% of these boots are manufactured in country A. What is the probability that your boots will last 1,000 miles? Well, here's how this works. We simply plug those numbers into this equation. What you can see after you do the math is that you have a 98% chance that your boots will last 1,000 miles. I wish mine would. Now, let's look at a more complicated example, one where we're estimating the probability of an event that occurs inside and outside the sample space of the second event. This requires a slightly more complicated formula to do it. Imagine that a particular medical test is 95% accurate. If someone has the disease, the test will report a positive result 95% of the time. Further, if someone doesn't have the disease, they will receive a negative result 97% of the time. Only 1% of the population has this particular disease. What is the probability that a particular person chosen at random will be tested positive? So what we're going to do is we're going to let TP denote the event that a person is tested positive. D will denote the event that a person has the disease. D prime will denote that the event that the person does not have the disease. Then it follows, we do the math, and what we find is that the probability of having the disease, remember, is 0.01. Then the probability of not having the disease, the complement, is 0.99. The probability of testing positive when you have the disease is 0.95. And the probability of testing positive when you don't have the disease is 0.03. So you just plug those pieces of data into the formula, and your result is 4%.